This video covers the preparation and reactions of ethers. Industrially, ethers are prepared via acid-catalyzed dehydration reactions. This involves the treatment of an alcohol with concentrated acid to produce an ether plus a molecule of water for every ether that's formed. Let's take a look at this mechanism, which is basically a bunch of proton transfer reactions and an SN2 reaction. We'll start with the hydronium ion because that's always present when we have concentrated sulfuric acid, and we'll use that to protonate our alcohol. We now have a very good leaving group. Water is a good leaving group, and that allows for the nucleophile on oxygen of another molecule to attack that electrophilic carbon and displace water, giving us the protonated ether and water as the products. Now either another molecule of water or a molecule of ethanol can deprotonate that protonated ether, giving us the neutral ether and the protonated alcohol, or if you had used water to do this, you would write H3O plus as the product. The chemist in organic chemistry laboratory generally uses the Williamson ether synthesis to create ethers. Generically, this reaction involves the treatment of an alcohol with a strong base, such as sodium hydride, and then treatment with an alkyl halide to incorporate an R group on the other side of the oxygen atom. The first step in this reaction is alcohol deprotonation. The second step is an SN2 reaction. An example of this reaction is one in which we take tert-butanol, treat it with sodium hydroxide, and then treat it with bromomethane to get the ether product. This CH3 group is the CH3 group out here. Let's take a look at the mechanism for this example. First, we have hydride from sodium hydride, write that lone pair, and use that to deprotonate the alcohol. Now you get an alkoxide. What does that want to do? It wants to attack, in step 2, the electrophilic carbon atom connected to bromine, a good leaving group, and now we get the formation of an ether and displace bromide as the leaving group. What happens if the starting materials were tert-butyl bromide and methanol? Let's put the methanol as the starting material, treat it with sodium hydride, followed by the alkyl halide. Do we get this product? No, this reaction does not work. What happens instead? Let's take a look at this. Put that lone pair on the hydride. Do your acid-base reaction to remove a proton from methanol, and now you get the methoxide, hydrogen gas, and then in the second step you treat the methoxide anion with tert-butyl bromide, and this is what happens, this undesirable outcome. You have a strong base and you have an alkyl halide with a good leaving group, but we know that we cannot accomplish an SN2 reaction on a tertiary alkyl halide. So those are not arrows that we can draw. I'm going to erase them. Instead, when we have a tertiary alkyl bromide, what we can do is an E2 reaction. So here our methoxide serves as a base that removes a proton, forms a pi bond, and bromine departs. And now we have methanol that's neutral. We have the 3 carbons as part of an alkene, and bromide is the anion. So what happens instead is an E2 reaction. This gives us a rule. You can't form an ether in basic conditions using a tertiary alkyl halide. And you can say because E2 will occur instead. Our next reaction is alkoxymercuration demercuration. And before we get into alkoxymercuration, I want you to recall oxymercuration demercuration from section 8.6. In that section, we took an alkene and treated it with mercury acetate and water, then sodium borohydride, and we get the following alcohol that is the Markovnikov product, meaning that the substituent goes on the more substituted carbon. This product is a result of the following reaction mechanism. I'm going to start this at the mercury ion, this cation. In this intermediate, on the carbon that's in green, that contains more of the positive partial charge because you can stabilize the partial positive charge at this tertiary carbon more than you can at the primary carbon. Water attacks. We break that carbon-mercury bond, and now we form an intermediate with a positive charge on the hydrogen, on the oxygen atom. In the next step, we use a molecule of water to remove that, giving us the neutral alcohol. Then in step 2, we've added sodium borohydride. And remember what we said about these boron-hydrogen bonds. These are nucleophiles. And this is going to serve as a nucleophile to attack the carbon containing mercury, and that departs. And we have our new product wherein we have a hydrogen atom that's gone on the less substituted carbon. So, what happens if water is replaced with an alcohol? Here is a generic reaction. Not generic, it's got specific reagents. These are exactly like what you've seen before in the oxymercuration demercuration, except for now we have methanol instead of water. That gives us a different product where instead of water adding across a pi bond, we have methanol adding across a pi bond. In our reaction mechanism, we first form the mercury anion, or cation. Then in our second step, the alcohol attacks the carbon that contains more of a partial positive charge, breaking that carbon-mercury bond, leaving us with a positively charged oxygen atom. We can use a molecule of methanol to deprotonate that ether, giving us a neutral compound. And then in the last step, we're using our boron-hydrogen bond to attack. Oh, let's see, I've left out a carbon here. This should be there. We're going to use that to attack the less substituted carbon, kick off the mercury acetate. That gives us the ether shown above. And so what you've done is added methanol across the pi bond. Let's take a look at an example and predict the reagents that would need to accomplish the following transformation. Here we've got an alkene and the product is an ether, and what might help us is if we draw the other proton that was included as part of the addition across that pi bond. We want to add methanol across that pi bond. So we want to do an oxymercuration, demercuration. And in step 1, we need to add the alcohol that we're going to add across the pi bond. So we want to add methanol, and then we need sodium borohydride in step 2 to get rid of mercury. Next, in section 13.6, we have reactions of ethers, and the first one is acidic cleavage. The general reaction for that is that you take an ether and add an excess amount of HX, where HX is a strong acid, where X is a halide, and then what we do is one of the R groups goes with one halide, and the other R group goes with the same same type of halide, and water is also produced. Let's look at an example. We take the molecule, this dialkyl substituted ether, and treat it with an excess of hydrobromic acid. Here we get two equivalents of the molecule that's the alkyl halide. And let's trace those carbon atoms. So there we've got 1, 2, 3, 4 carbon atoms, and in our product we have 1, 2, 3, 4 carbon atoms. So this oxygen group is replaced with a bromine, and there are 2 of those in the product because our ether is symmetrical. If our ether were not symmetrical, we would get 2 different products. Let's take a look at the mechanism for this one. In step 1, we have a protonation of the ether. Whenever you see a strong acid and an ether or alcohol, anything with an sp3 hybridized oxygen atom, you want to protonate that alcohol or ether. Then we form a cation intermediate and the bromide that's the leaving group. In our next step, knowing that bromine is a good nucleophile, and now this entire part of the molecule is a good leaving group, we take our good nucleophile and do an SN2 reaction. And that gives us our alkyl halide on one side and the alcohol on the other. Next, we treat our alcohol with the strong acid, forming this cationic intermediate. And again, look, we've got bromide, our good nucleophile, that attacks the carbon containing the leaving group and displaces water. So now our product is that alkyl halide plus water. For acidic cleavage to occur, you must have sp3 hybridized carbon-oxygen bonds. Let's take a look at this following example to show why you only get one bromide as the product and the other one remains an alcohol. And the mechanism for this reaction, the first step is to protonate the oxygen with our strong acid. And then we have bromide as a spectator anion, which was the leaving group. Bromide can now attack the sp3 hybridized carbon. And we get the neutral molecule methanol plus our alkyl bromide. So this is one of our products. Then what do we do with this alcohol? Well, knowing that we're in strong acid, so we have HBr to go to the left side of this equilibrium, we can protonate the phenol, and it will indeed be protonated. But we can't undergo an SN2 reaction at this position, so that means that we cannot form, or we cannot undergo a second SN2 reaction. Thus, our phenol stays phenol. And that is all I have for you today. Have a great day and let me know if you have questions.